Well, g'day, I'm going to assume that you've built or have bought one of these water models of electricity. One of the things I like to do when I set this up with students is to not start with it like this full. Start with it empty and discuss how important it is for the pipes to be full of water for this to actually model electricity. And it does take a while to get rid of the airlock, make sure that you get rid of any airlock that is in that tube there. And the reason for that is that electrical wires are not empty of charge. They're already made up of atoms, and atoms make up everything, and atoms have got charge in them. So when you've got a wire and you push an electron in this end, they all roll over and a different electron falls out that end. That wave of negative charge propagates along that wire at close to the speed of light, even though the individual movement, the individual drift velocity of the electrons is around about walking pace, a nominal difference in speed. And of course, at the same time that a region of negative charge propagates through the wire this way, a region of positive charge propagates also at close to the speed of light in the opposite direction. Which is why it's really critical, first of all, to think of the pipes as already full of water. And it means that it doesn't really matter when we talk about conventional current. Often that really annoys students. Why don't we just talk about electron current? Well, because electron drift is really slow. It's the propagation of charge, and the propagation of positive charge is the mirror. So really it doesn't matter which one we talk about. And so we continue to talk about conventional current as the flow of positive charge from the positive terminal of the battery to the negative terminal of the battery. So let's talk about quantifying those really important concepts. And the first, of course, is to get a current flowing, which I'm going to do by the two levers that I've got to make that current flow. And I can quantify the current by measuring the amount of current that goes into there, first of all. But before we talk about current, because current really is the effect, let's talk about the causal factors. So a great little demo to do is to put an addition to the outflow pipe, open the valves, and after an initial flow of current to fill up the extra wires here, you can see that the current stops because the electrical potential energy here is the same as here. There's no difference in electrical potential energy, or in our model, no difference in gravitational potential energy. And it's that difference that generates the force, the electromotive force, on the charges to move in the first place. So it's only when there's a difference between here and here do we see our charges moving in the first place. So that's a really important concept. Voltage is a difference, which is why I always like to get my students to talk about using terms like voltage across or between. The minute a student talks about the voltage flowing through, you know that they've misunderstood what voltage is. It's a difference across or between. And we can see that visualized in these vertical risers. So here is my open switch, closed valve, but an open switch. And you can see I've got the full potential difference of the battery across that component. Nothing across my low resistance component, no current flowing. And don't forget, of course, that you can vary the height here and change the total voltage of your power supply and play with the effect that that has. So voltage is one of the levers that we can pull to influence current. And the second one, of course, is resistance. So let's reduce the resistance of this component and get a current flowing. So first of all, we can quantify that, and just a nice easy way to do it is just to collect some water. Make sure you keep the exit of that pipe at the same height as you move it across. And so that would give me, I know that's 140 grams of water, and I can work out how many grams per second, which is how we measure current. It's the amount of charge per second through the circuit. And of course, because it's a full pipe, the volume through here is the same all the way, so it doesn't matter where we measure it. And you can hear that the pump system now has to work harder to maintain that voltage difference. So that's one of the levers we can change. We can change resistance. The other one is we can change the pressure, the voltage difference between one side of the battery and the other. And so now, with less voltage, less difference in electrical potential energy, there'll be less EMF on the charges to move, and so therefore we should measure a lower current. And we can do that. We can make that prediction. We can kind of see it intuitively, and then we can actually make some quantitative measurements of that. And of course, the joy of having two components in series is I can increase the resistance of this one as well. And you can see what happens as the voltage across this component increases. And the total voltage drop between the input and the output is the same as it was before. The voltages in a series circuit add up. So a bunch of ideas to get you started there with your class is a great discussion. And I think this model is good to have little pieces of it and then go and do some real circuits and come back to it. And so what I'm going to show you in my next blog is how to use this as a model that students can interact with so they can learn how scientists deal with models. What do we do when we invent a model that we think models some real phenomenon? What do scientists do? and let's play a little bit of that, because that's a teaching above just electricity and really teaching those fundamental skills of working scientifically.